So that we are now ready for our third paper, identification of F1 and F2 in speech using modified zero-frequency filtering, which is going to be presented by RaviShankar Prasad from Idiap. Yeah, we're exactly on time. So, yeah.
All right, good morning, everyone. I am here to present my work on identification of F1 and F2 in speech using modification in zero-frequency filtering. I'm RaviShankar Prasad, and this work has been done with Mathew at Idiap. So, yeah, we know that speech is seen as a result of a time-varying source acting on a time-varying system component. And to study this source and system component, we use appropriate modeling techniques to decompose the source and system characteristics. Formants are basically the resonances or characteristic components in the system part of speech, and they are usually used to depict a lot of linguistic and paralinguistic elements in speech. Formants are quite useful. The first two formants are especially useful to study a lot of speaker and speech-based characteristics. So, formants follow generally two major line of definitions. First is that they are understood as absolute or relative peaks in the spectrographic representation of speech, and the second definition imposes that they are understood as characteristic resonance poles in the transfer function of the supraglottal vocal tract. So both these definitions are aptly chosen by different modeling techniques, and here we can see that in this case we have the DFT spectra along with the autoregressive spectra obtained for different speakers, the male, female, and child speaker, and for different vowels. We can see that appropriately formants from both these definitions mostly align. So extraction of formant frequencies usually follow a two-step process. The first step is to generate appropriate candidate frequency locations from a spectrographic representation of speech. The representation can be obtained in time domain by linear prediction and also in frequency domain by probably the DFT spectra or some other appropriate spectra, and in the Kepler domain as well. Formants are the second step in prediction of formants follows a continuity constraint to be applied on these candidates and choosing an appropriate candidate from the set. So the continuity constraints also are known as the application of continuity constraint is also known as tracking routine, and the tracking routine ensures that the contour of formants thus obtained over successive frames is smoother for different sounds. And the tracking routine are implemented usually by popular methods like dynamic programming, hidden Markov model, Kalman-based filtering, and distribution-based or neural network-based methods. So the proposed method in our paper basically uses a method called zero-frequency filtering. The advantages of using zero-frequency filtering is for format identification is we do not assume a model to decompose speech, and also like it is a tracking-free kind algorithm where we do not generate multiple candidates. So zero-frequency filtering is popularly known as ZFF. It has been introduced for studying source characteristic in speech. It is realized as a resonator which is centered at 0 Hz and has a very sharp bandwidth. So it has a very large decay. The resonator is realized as an integrator, and therefore the resulting filtered signal exhibits a polynomial growth trend. And the trend is removed in the next step, which is also known as the trend removal step of ZFF, where we choose an appropriate window for the mean removal from the signal. And the duration, the important part is the duration of the trend removal is chosen between the first and second multiple of the fundamental period of the signal, so that it gives a peak at in the spectrum, it gives a peak at the fundamental frequency of the signal, and that's how it gives us source characteristics. So here is a illustration for the process. we can see that the speech signal is passed through the zero frequency filtering mechanism to obtain xn, which is the signal with the growing trend, polynomial trend, and then it is removed with the help of the trend removal window, and we get the signal yn, which is periodic or pseudo-periodic. It depends on the fundamental period of the speech. And we can also identify the glottal closure instance in this zero frequency filtered signal. Now the trend removal window has a response which is given by equation 4 and 5. This response is more like an inverted moving average filter. So what we did is we can change the duration of the window of removing the trend, and we see that the peak of the response, it shifts to higher frequencies. So if we maintain it at the fundamental period, the peak is given by the black curve, and it is maintained around the f0 of the signal. But as we change the duration, make it shorter, which is the 2n plus 1 is the duration of the trend removal window in equation 4. As we maintain it shorter, the peak, the corresponding peak in the spectral response start moving forward to higher frequencies, like the blue and the pink curve. So also while moving forward, it exhibits a higher bandwidth. So if we appropriately shift the trend removal response in the formant region, we can actually highlight the formant characteristics in the resultant signal. The advantages of using this is, this particular filter along with the zero frequency filter, the zero frequency resonator, gives a spectral emphasis on the formant region, and it also mitigates the rest of the spectral information. So we choose to experiment with synthetic response. We designed a synthetic response here in the first figure, which is given by the red curve, and the response has peaks at 80 hertz, 450 hertz, and 3.7 kilohertz, which are essentially chosen in the first f0, f1, and f2 regions. And then we use the train of impulse to excite this cascaded set of resonators. And then we use the modified ZFF filtering approach to derive the characteristics, formant characteristics from speech. So we see that the three filtered signal, which is the black, the blue, and the red, the magenta one, we can see that the black one is a regular ZFF signal which has a peak at the f0, which is around 80 hertz. The blue signal, which is a shifted trend removal, shifted with a trend removal of 1/10 of the period, 1/5 of the period, exhibits a peak in the f1 range, which is around 450 hertz. And we can see that the magenta one, which is 1/10, the duration is maintained at 1/10 of the regular trend removal, is showing a peak at the second formant around 3.7 kilohertz. So we also experimented on speech, human speech, and we see that in the lower figure we have spectrograms where the first spectrogram depicts the regular DFT-based transformation, and the second B and C, the figures B and C. I'm sorry, I'll have to point it here probably. Okay. So the figures B and C, they depict the first and the second trend removed components, and we can see that in figure B we can see a formant component prominently visible in the spectrogram, whereas for C we can see the second formant component prominently visible in the spectrogram, which gains prominence by these two different shifts in the trend removal. So we proposed an algorithm based on our observations. We take the speech, and a regular ZFF will give you a component which is primarily the source component. But when we trend removed with respect to like the fundamental period by 5 or 10, we get the first and the second formant components in speech. So this is how it works. The speech signal, we can see that the first component, which is achieved by the ZFF, is a fundamental frequency component, and this is the second and the third filtered components, which are essentially the formant information component. We can also see this in corresponding spectrograms, spectrums we obtained using DFT. The red one is imposition of the linear prediction response of this particular signal. And we see that in the first component, the F0 component is in the DFT, the blue, which is the DFT representation. The F0 component is prominent, whereas in the second and third filtered signal, the F1 and F2 components gain emphasis. So yeah, we tried to validate our observations on 2 different data sets for typical and atypical speech. We used TIMIT-VTR dataset where the formant contours have been hand marked for a certain subset of TIMIT. And we also used the PC-GITA database where atypical speech by Parkinson's patients is present. So the F1 and F2 contour which we identify are derived from any, we can use any generic spectrographic representation on those filtered signal to derive the spectral peak in F1 and F2 range. And we do not apply any smoothing constraint or anything. And the proposed approach is compared against state-of-art methods, which are like wave surfer, PRAT, and Kalman filtering based method, and MUST is a bandpass filtering. Bandpass filtering based method, and TVQCP is basically a linear prediction, weighted linear prediction based method. And the results are evaluated based on the formant estimation error, which is basically an average error of deviation of the formants from their actual noted position. And there is another error called formant detection rate, which considers a window of a bandwidth in the spectrum to determine if it is the correct detection or not. So on TIMIT-VTR, we explored the first and second formants, and we compared it with the baseline annotations. So here in this figure, we can see that the red annotations, red dots are ground truth, which are marked every 10 millisecond window. And we derive formants from our method, and they are compared against the red marks. And they are also derived every 10 millisecond non-overlapping window. So the upper figure gives the first formant contour, and the lower figure B gives the second formant contour. And yeah, this is how the results look on the VTR data set. If we compare our formant estimation method with over formant detection rate and formant estimation error with different methods, we can see that we have a fairly good formant identification in the first and second formant. So FDR1 is for first, FDR2 is for second. The second formant annotations are also, in TIMIT-VTR, they sometimes correspond to spectral peak, sometimes not. That's why somehow we get, a little bit lower rate. But yeah, the first formant detection is quite high when compared to other methods also. Other methods also, yeah, perform similar. And for the PC-GITA database, we tried to derive a Wobble triangle because in atypical speech, especially in Parkinson's, there are motor disorders and which lead to troubles in articulation of formants. That's why they lead to expansion of the formant triangle, the Wobble space area. So we tried to plot this Wobble space area derived by our method versus other methods for typical and atypical speech present in the PC-GITA database. And the first one is the Wobble triangle, which is obtained by the clusters for the clusters for 3 different vowels by our method, and there are other methods. So we can see that the cluster obtained by our method is a bit unconstrained. That's why it's quite scattered. The constraints imposed for formant tracking and identification by other methods can be seen in the clusters. And if we compare the vowel space area, we can see that the proposed method gives larger enlarged vowel space area for Parkinson's patients, which is similar to other methods. So it's a lightweight method. It's implemented in time domain. It's tracking free. It's model free. And yeah, the only catch with this method is like we cannot shift the trend removal peak response to higher frequencies because of the bandwidth expansion, and we lose the resolution on higher formants like F3 and F4. So yeah, it is used only for F1 and F2. So that's all from my side. Few references I used for my talk, and thank you.
So, any questions for the speaker.
Maybe one question. Can you estimate also the bandwidth of the formants with that? And have you tried it?
So bandwidth estimation is a bit tricky because formants are being identified as a cumulative peak of the response filter and the spectral peak. So this cumulation basically alters the resultant bandwidth. So this method cannot result in a true bandwidth, but yes, if we use like there are certain ways to identify bandwidth with respect using the amplitude of the resonances based on group delay calculations. So if we use the group delay representation on the resultant signals and we identify the amplitude, maybe we can estimate the bandwidth. I didn't try that, but yes, I know that can be employed.
Okay, and can it work also to estimate anti-resonances?
Anti-resonance, that would be tricky because it's totally based on the resonator. So
okay, let's try to invite a raised hand. No,
Doesn't seem to work.
seems to be difficult. So in the meantime, question from what I understood, you are using an estimate of the fundamental period to find the right time windows, put it that way. How sensitive is the algorithm to this estimate?
well, earlier as we modulate the duration of the trend removal filter based on the fundamental period, we thought it was sensitive to the fundamental period. But later we did some more experiments to see that if we have a very bad estimate of the fundamental period, but even within a valid range, we can actually shift the response, trend removal response appropriately. So it's not very sensitive to the determination of fundamental period. That's what I'm trying to say. But it is just that if the fundamental period is too small, maybe the modulation to it would be smaller, even smaller, and that's where maybe for special cases like singing voices and all, or children's speech, maybe for now we have seen that it performs well for children's speech, but maybe for more infants or that kind of speech, it may give some trouble.
Also, for high-pitched voices, do you see any problems in confusion between the first formant and F0?
No, actually not. So the interesting thing was I had another plot. I will append it to the presentation later. So we see that within the valid first and second formant ranges, especially the lower first formant ranges, it didn't interfere with the fundamental frequency peak until unless it is really in fact interfering with it. Like if you have a very high pitched voice with a very low F1 sound, then maybe it's practically difficult to resolve those. And otherwise we didn't have any problem with because we did see in the 300 to 400 hertz sounds with F1 in that range, and it was doing quite well. So there was absolutely very small error so in that range. Yeah.
One final thing is a comment by Roger Moore, complimenting you on your work, but it's also commenting this applies only to voice speech, or?
Yeah, it applies to voice speech, especially formants in the lower frequency range, like mid and low frequency range, yes.
Any further questions from the audience? We don't seem to be able to hook up with the remote. Okay, let's thank the speaker again.
Thank you.